Hi everyone, it's Miss H, and today we're going to continue talking about energy, and we're going to be looking at thermal energy. So what is thermal energy? Well, in order to understand thermal energy, there's two terms we really need to know, and that is heat and temperature. So thermal energy, we oftentimes say, is the energy associated with heat. So what is the difference between heat and temperature? Because these are two terms that we oftentimes get mixed up. So temperature is a measure of the average kinetic energy of the particles of a substance. The faster the particles are moving, the higher the temperature is. So when we're talking about thermal energy, we're talking about the sum of the kinetic and potential energies of the individual atoms or the individual particles that make up the substance. So temperature is a way to measure how much thermal energy it has. Temperature depends on the material that the substance is made of and what its mass is. So the more mass that it has, you're going to have a different kind of temperature, and different substances are going to change temperatures easier or harder than others. Heat is the transfer of energy from one substance to another because of differences in temperature. Thermal energy will always flow from the hot substance to the cold substance. So if you think of heat as, or if you think of temperature as like money, you know, if it's a hot object, it has a lot of money. It's like having a lot of money, and so that hot object can afford to lose some of its heat and give it to the cold object, just like somebody who has a lot of money can afford to give away some of their money to the person who doesn't have any. It's that same kind of idea. So there are three main ways that energy can transfer from one object to another. The first is called conduction. Conduction is the transfer of energy through direct contact. So I cannot conduct my heat to something unless I am touching it, and it cannot conduct its heat to me unless it is touching me. So because of that direct contact requirement, conduction happens fastest in the solids, and it's basically non-existent in gases because the particles are not in direct contact with each other. So an example of conduction would be like touching a hot pan. When you touch the pan, it immediately conducts its heat into your hand. A thermal conductor is any substance that is good at transferring thermal energy. It transfers that thermal energy easily. It will release that heat very easily. It doesn't hold on to it very well. So it changes temperatures very quickly. Examples of thermal conductors are pretty much any kind of metal, because we know that metals heat up and cool down very quickly. A thermal insulator is a substance that is poor at transferring thermal energy. It holds on to its thermal energy, so it doesn't change temperatures very quickly. When you touch it, it doesn't necessarily immediately feel hot or cold because it takes a while for that energy to transfer, that heat energy to transfer between your body and that object. So examples include things like rubbers, plastics, wood, air, things that you don't necessarily immediately notice a temperature change with. So for example, you know, you put on rubber or silicone oven mitts, or you have plastic or rubber insulation around your wires to help prevent that that energy from moving out of there. So thermal insulators are not going to change temperatures quickly. So a good example here is you have two pans of brownies that you're going to put in the oven, and one of them is in a metal pan and one of them is in a glass pan. And when you pull them out, the metal pan is going to cool down much quicker than the glass pan is because glass is an insulator, so it doesn't change temperatures as quickly as the metal does. The second method of energy transfer is convection. Convection is the transfer of energy through mass movement. It can only happen in fluids, which means it only happens in liquids, gases, as well as what are called amorphous solids. An amorphous solid is one that it's technically a solid, but it still has a loose enough connection between those particles to behave like a liquid. So Jell-O would be an example of an amorphous solid. It can wiggle, it can move around, that sort of thing. Glass is actually also an amorphous solid. That's why in really old buildings, the glass at the bottom of the window is thicker than the glass at the top of the window because that glass is very slowly flowing down. So if you wanted to see an example of convection, you would put like a single macaroni noodle into a pot of boiling water, and you can watch the noodle bob around in the convection currents. Other examples of convection include our ocean currents, air currents, and the movement of molten rock inside the mantle's crust. So all of those are things you probably talked about in earth science if you've already taken that. And so this is talking about, you know, the hot air rises, the cold air falls, the warm water goes up, the cold water comes down. So it's that difference, that movement based on temperature. And so you don't necessarily have direct contact between the two things. The top of the water is not necessarily in direct contact with where the bottom of the water is, but where the heat source at the bottom is. In the pot of water, but because it causes that water to move because of changes in density and that sort of thing, it actually helps to distribute that heat elsewhere. The final method of energy transfer is radiation. Radiation is the transfer of energy through waves. It is very different than the other two methods in that it does not require any material to travel through. So conduction, you have to have an actual physical substance, particles that can actually interact with each other in order to have that touch happen, in order to have that heat transfer. Same thing with convection. Even though the heat source might not be in direct contact with the part that's being heated up, there still have to be particles there that can bang into each other and eventually transfer that heat across. With radiation, you don't have to have that because radiation travels in waves, which means that it's actually capable of traveling through the vacuum of empty space. And so this is how we get our heat and light from the sun, because that's how that energy comes to us from the sun, because there's not enough particles in empty space in order for us to get that heat and light otherwise. So again, that's our example, is the transfer of heat and light from the sun to the earth. A couple of key things you got to remember about radiation. All objects, regardless of their temperature, radiate out energy. So if you've ever looked at something like a thermal imaging camera, you'll see that even though the table and the chairs and that sort of thing are cold, you can still see them on the thermal imaging camera because they're still radiating out energy. They're still radiating out heat. It's just a lot less than what we do. So humans radiate out more heat than tables and chairs and pencils and textbooks and that sort of thing. But then other things like computers might even be radiating out more heat than we are. And so you can actually see those differences in the thermal imaging camera. Hotter objects radiate out more energy than colder ones. So that's again what we're talking about there, where the higher the temperature is, the more energy you can afford to get rid of, and so the more energy that you're going to give off. And eventually, both substances are going to end up at the same temperature. And this actually doesn't apply just to radiation. This applies to all methods of energy transfer. So whether we're talking about conduction, convection, or radiation, eventually the two substances that are interacting are going to be the same temperature. Another thing we want to talk about with this methods of energy transfer is thermal expansion and contraction. So if something is expanding, that means it gets bigger. If something is contracting, that means it gets smaller. So with thermal expansion, the volume of the substance or the size of the substance increases because of the temperature increase. With thermal contraction, the volume of the substance decreases because of a temperature decrease. So if you've ever looked at like a floor or a sidewalk or that kind of thing, you'll notice that there are these breaks in the around the edge of the floor or in between the blocks on the sidewalk. And those are thermal expansion joints, because in the summertime, when the temperature goes up, those blocks actually are going to swell up and get bigger because of thermal expansion. And so it actually gets to the point where if you didn't have those breaks, the blocks would bang into each other and crack. And so by having those joints there, you prevent that from happening. And then in the winter, those joints become more pronounced because as it gets colder, the blocks contract. And so those expansion joints actually get bigger. They get wider because of the fact that the substance has gotten colder and contracted up. So this is there's some really good videos out on YouTube that you can find to help you see visuals of this, because most of the time thermal expansion and contraction are too small for us to notice with the naked eye. But thermal expansion and contraction occur more in gases than they do in solids. So if you want to see an example, take something like a balloon and blow it up and stick it in your freezer. When you put it in the freezer, you'll see that it actually does shrink down, because gases, because of the way their particles are, have the ability to expand and contract more than solids and liquids do. If you take that same balloon and stick it out in the sun, you'll notice that the balloon gets bigger. The last thing we want to look at is specific heat, and we're not going to go into a great amount of detail with specific heat like you would in some more advanced classes. So for us, we just really need to know the definition of specific heat. So specific heat is the amount of heat that needs to be added or removed from a substance in order to change the temperature of 1 gram of that substance by 1 degree Celsius. And there are formulas out there that you can use to figure out what the specific heat is and the amount of heat that would need to be added to cause a change in temperature or removed to cause a change in temperature. But we're not going to get into that much detail. All we need to know is that Specific heat is that amount of heat that needs to be added or removed in order to change the temperature of the substance of 1 gram of the substance by 1 degree Celsius. The greater the specific heat is, the more heat that you have to add or remove to cause the change in temperature, and the slower the temperature will change. So thermal insulators have very high specific heats because they're not going to change temperatures very quickly. They do a very good job of holding on to their temperature, so it takes a lot of energy to cause that temperature to change. Metals tend to have lower specific heats because they tend, so those thermal conductors, because they tend to gain and lose heat very quickly, and they tend to change temperature very easily. Water is an example of another thing that has a very high specific heat, and this actually leads to a lot of really interesting things, like having coastal cities that have a lower temperature variation than inland cities, because that water actually helps to regulate the temperature. It's also why water takes such a long time to boil, because it takes a lot of energy added to that water to get it to change temperature. So that kind of sums up all of our thermal energy stuff. The last thing we want to look at with that, though, is thermal energy diagrams. How do we represent thermal energy changes visually? So we're going to take a look at 2 thermal energy diagrams here. In the first one, we're going to hold a cup of coffee. So you've got your thumb on one side and 1, 2, 3, 4 fingers on the other. Okay. And so our cup of coffee, of course, is going to be the hot object, because it's hopefully we're assuming that we're holding a hot cup of coffee here. That's what we say in the thing. Okay. Our hand is going to represent the cold object. And we know that heat always moves from hot to cold. So heat flows from the cup into the hand. So heat flows from the cup into the hand. Okay, in the second one, we have a glass of soda that we've added some ice cubes to help cool it down. So we know that our ice cubes are colder than our soda is. So our soda is going to be our hot object, and our ice cubes are going to be our cold object. And again, heat flows from the hot to the cold. So heat flows from the soda to the ice. So why does ice cool down a warm drink? It's not because cold is flowing from the ice into the drink, because cold is just the absence of heat. So you can't have cold flowing. Cold is just the lack of heat. The way that ice cools down a warm drink is that the heat leaves the drink and goes into the ice, or you can think of it as the ice is stealing the heat away from the drink. It's also why ice feels cold in your hand, because it's stealing the heat away from your hand. So when you're asked the question, how does ice cool a warm drink? Ice cools a warm drink because the heat flows from the drink into the ice.